Alright, Assalamualaikum. Apa khabar semua? So, today I'll cover two topics. One is the regression models for count data, and the other one is regression models for rate data. So, the link to the files and datasets will be available right down the YouTube video. I'll provide the link inshallah soon. So first let's talk about regression models for count data. um, you know that um, number of times an event can occur is a common form of data, right? So when the outcome is count, then one of the popular model is the Poisson regression. um, Sometimes um, the count is modeled as rate, but that one we will cover in the next lecture. So this one we will deal with only count. um, this is the Poisson regression model with the probability distributions written as this. um, if you look at one of the example from Introduction to Generalized Linear Model by Dobson. So this is an example of data that have been tabulated. So you see that this is the number of tumor type at different site. So for example, the Hutchinson melanotic freckle on the head and neck, there were 22. Nodular tumor on the trunk were 33. So imagine this, you have a column of site, a column of tumor type, and a column of frequency. You have to imagine the kind of dataset that um, were originally used to come up with this table. So this is the link functions for Poisson model, which is log mu jk equal log n plus log theta jk. So the R codes for Poisson regression is simple. Okay, it's simple. You use this GLM, and this is the um, outcome variable, and it's supposed to be in count integer, and these are the predictors. Here we specify that there is an interaction between variable site and tumor. So the predictors for this model include site, tumor, and the interaction between site and tumor. We specify family as Poisson, and specify the data set. Right. So this is the saturated model where you have all predictors included in the model. You may have an additive model where not all of the variables are inside the model, and no interaction. And the minimal model is a model where you have only a constant, okay, no other predictors. So this is in table 9.10, thing in the same book where this model was run from this data set. um, yeah, I highly recommend that you read this book. Not a thick book, very simplified um, introduction to Poisson regression, but a little bit heavy on the notations and all that. So yeah, that's one of the advantages. So you have this the saturated model where you have um, the site and the tumor type and the interaction. This is the additive model where you have only the site and the type of tumor, and this is where you have nothing as predictors, and then you'll get the intercept constant. So, so this is basically the log count, the log of count, okay, the log of count. So the exponentiations of the values, for example, exponentiations of 3.507, right? So you get 33.35, this one, but this is so this is the expected frequency with no predictors, right? Okay. So for the additive model, the expected frequencies for um, the hem melaninic freckle, okay, melaninic freckle, because um, the baselines for this, okay, the baseline for this group is basically Hutchison melanotic freckle, HMF, okay. So where every other things are zero, um, then the expected frequencies for HMF on HNK, because the the baseline for side is head and neck, okay. So if um, everything else is zero, not superficial, not nodular, not indeterminate, not trunk, not extremities, so you have the expected frequency or expected count of 3.35 um, on the minimal model. The additive model is 5.78, and on the saturated model is 22. So the you exponentiate this one, all right? Um, for the expected frequencies of intermediate indeterminate tumors or IND in the extremities, then again you have to um, look here. So let me check if I got this right, okay. Indeterminate should be, let me check about the minimum model, right? The additive model is exponentiation 1.75 and 0.499, which is this one here, okay. And then the search, and then 0 1.201, which is this one on the extremities, and indeterminate, okay, indeterminate and on the extremities. On the saturated model you have -6, this one indeterminate, and extremities and the interactions of indeterminate and extremities. Right. Since they are all dummy variables, so if it's present, then it is 1. If it doesn't, then it equals 0. So model assessment wise, you can look at the Pearson residuals and deviance residuals. So look at the goodness of fit and also the deviance. Right. If you look at the practicals, so I load tidyverse libraries for data wrangling and data visualization. Haven, if you want to read statistical software dataset from Stata, SPSS, or SAS, Broom to tidy your output, and Janitor to clean the names of the variables. So I read a dataset named COUART2.dta. So it's a Stata dataset. Okay, and I name this dataset as publish in R. There is another dataset which is NMES 1988.csv. So for that, I use read underscore csv, and I use pipes and clean names from janitor package to make pattern names for the variables. Um, then I use glimpse to look at the variables and the observations. So we have variable ART, variable FEM, MAR, KIT5, PhD, and MENT. So DBL refers is actually a double variable. FEM double plus label, it means that it is coded as 0 and 1, but 0 and 1 uh, are basically labels for something. All right. So so what I do now is what I did is use the function mutate underscore if. So where if the variables are label variables, they will be converted or generated as factor. So then I use summary to get the quick summary statistics, and then I use ggplot, dataset publish, and the variable of interest is ART. I think this is the number of article. Okay, the number of article. The dataset is the dataset came from a study where they look at factors that influence the number of articles published by academicians. So they study whether gender, female or male, marital status, kids, number of kids or children, whether the number of PhD. I'm not sure, but what's that? And then does it refer to an MENT? I think mentorship, perhaps. Okay, so if you look here, and then so I use ggplot and I plot histogram, so you can see this skewed to the right, which is typical of count distribution. Um, and let's assume that the outcome, which is the distributions of the number of articles, number one follows the Poisson distributions, and they are random observations and also independent, and they have they fulfill the linearity in parameters, and mean equals variance. Um, then it's good to run Poisson regression. We can start off with the constant only model, no predictors. So you write GLM ART tilde 1 family Poisson and link equal log. So this is the log link, and dataset publish and type summary. You'll get that you get this the log of the count. So it means this is the average log count. So since the value of beta naught equals 0.52, so when you exponentiate it, then you'll get 1.69. So that's basically the average of number of articles, all right? So which is actually same with the is similar with the mean 1.693. Okay, in a multivariable model where we try to look at the effect of female variable mar plus kid plus phd plus ment, um, using the Poisson log link, and when we run this summary, um, we see that women has the log count of minus 0.22, and married has the log count of 0.55, uh, if you in comparison to a single, um, with one increase in the number of kid, then the log of count change by a factor of minus 0.18, with one uh, one unit increase in PhD, then the log of count um, increase by a factor of 0.013, so on and so forth. So and you can convert this output into a data frame using tidy from a Broom package. We specify the conf.int equal true to generate the 95% confidence intervals, so you'll get this nice output. So the number of article, the expected log of count, which is this one, right? So if you look here, if you for women, on average they have the log of count for number of articles at a factor of minus 0.23 in comparison to men. It means that the rate of or the number of article for women um, actually less than men. If you and the number of articles for married scholar was on average 0.55, the log of article number compared to single scholars. From the log of count, you can exponentiate this to get the rate, okay, the rate for a unit change in x. So for example, the for women, the the rate of number of article is 0.80, or the number of articles is 0.8. uh, let me rephrase that. Okay, let me rephrase that. So if you are a female scientist, okay, female or women, then you will decrease the expected number of articles by a factor of 0.799, holding other variables constant. Okay, so yeah, if you are women based on this study, then the expected number of articles is less than men, and it is less by a factor of 0.7988. If you are married scholars, then the number of articles, or the expected number of articles, um, increased increased in comparison to those who are single, and the increase in the number of articles is at a factor of 1.17. So it means that if the scholars are married, so they have more article, and the number of articles actually grow, or bigger, at a rate of, or at a factor of 1.17. Okay, at a factor of 1.17. If we use augment, this is from library broom, then you can generate the fitted values here. Okay, the fitted values here, which is the log of the number of articles. Okay, log of count. Okay, log of the number of articles. So that's the reason why you have negative values here. If you want to get the predicted number, okay, predicted count of article, this is predicted log of articles, this is the predicted count of article, then you can use the function predict and your model, and type equal response. So this is the number of the expected or predicted count of article. Okay, so for observation number 1 is about 1.96 article, observation number 2 1.29, 1.30, 1.32, so on and so forth. So you can do this manually. So what we do is, um, write down the intercept. Okay, this one 0.305 minus beta. So this is beta 0, beta 1, beta 2, beta 3, beta 4, beta 5, beta 0, 1, 2, 3, 4, 5. Okay. Um, this one, yeah, right? 1, beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. And then get the predicted log of count, and then exponentiate this number, and you'll get the what we call number of expected number of the uh, articles. All right. So And next, I'll talk about uh, um, the notes and the practical for rate.